Welcome to Pharmaceutical Calculations, a conceptual approach, Lesson 6, Density and Specific Gravity. This is a topic quite common in pharmaceutical sciences, and it's actually considered an easy one. However, the conversion of gravimetric to apothecary units or the other way around could prove quite challenging, and also, especially at the beginning, when you practice a couple of times, it becomes easier. And also the determination or the calculation of density of liquid pharmaceutical mixtures from pure ingredients could also pose a challenge at the very beginning. Let's start with our definitions as usual. So the density of a material is defined as the weight divided by the volume it occupies. The System International unit of density is kilograms per cubic meters. But in pharmaceutical sciences, we commonly use units of grams per cubic centimeters or grams per ml because pharmaceutical ingredients are usually solids. They don't expand that much as gases, and that's why we're using most conveniently grams per ml. Now, specific gravity is defined as the ratio of the weight of a unit volume of some substance to the weight of an equal volume of purified water at a stated temperature. We're going to see some of the formulas in a minute. Now, the specific gravity equals the density only when density is expressed in gravimetric units, in units of grams per cubic centimeter, for example. We are all familiar with the common formula of density, which is the mass of the volume, and mass is expressed in grams, kilograms, etc. But also, if you use apothecary units, it could be written in pounds or ounces or grains. Volume is expressed in liters and mLs, but also in apothecary units, it could be written as fluid ounces, for example. That's the symbol for fluid ounces. Now, the formula for the specific gravity is more involved, and it's basically, as you see, is the ratio of the density of the unknown substance over the density of water. So this is basically equal to the mass of the substance over the volume of the substance over the mass of the water over the volume of water. We usually use water as a reference to determine specific gravity of unknown materials because the density of the water is 1 and therefore the denominator cancels out. And now you can see why the specific gravity of a material equals its density when it's expressed in grams per ml. How do we measure in the lab? At least one of the ways to measure specific gravity of liquids and solids in the lab is using a pycnometer. And this is a vessel that could be made of steel, it could be made of glass, so you can see through. Could be made of a variety of materials. And basically, it involves 2 or 3 easy steps. First, you weigh the empty material, the empty dry pycnometer on an analytical balance, and you note down the weight. Then you fill the pycnometer with purified water up to the calibration mark, and this is important to fill it up to the mark, and weigh again. The difference between the two is the mass of the water, so that would be the mass of the water. Now you repeat the same procedure with your unknown liquid. And again, it is important to fill it up to the calibration mark with the unknown liquid. Why? Because, as you can see in the formula here, since the volumes are the same, they cancel out, and the specific gravity of the unknown liquid can be determined as the ratio of the 2 masses. Let us now move to some of the particular problems that are quite challenging. We're not dealing with easy problems in these lectures, they don't worth our time. So let's take a look for example 3.1. Calculate the volume occupied by 60 grams of olive oil if the specific gravity of olive oil is 0.92. So if the specific gravity of oil is 0.92, it implies that the density of oil is 0.92 grams per ml. And as you can see in the solution here, now that I know the density of oil, okay, I know my formula as well, that the density of oil is equal to the mass of the oil over the volume of the oil. So I solve for the volume of the oil, as you can see here. The mass of the oil is 60 grams, that's there. And the density of the oil is 0.92, and therefore 65.2 ml is the volume occupied by 60 grams of olive oil. And this kind of exercises could prove useful in a retail pharmacy or at a hospital if you want to choose a container to place your liquid formulation or prescription. So the size of a container can be chosen, of course, using the specific gravity information and the mass. Now the next one involves the conversion of units. So example 3.2 is asking you to express the density of the water in grains per fluidance. We know that the density of water is 1 grams per cubic centimeter or 1 grams per ml. And here basically I'm asking you to remember that 1 ml is equal to 1 cubic centimeter. There's no easy way to explain that mathematically or to prove that mathematically, but I encourage you to go back during high school physics lab exercises or chemistry exercises where you fill a certain container of unknown capacity with a volume of particular fluid. Definitely 1 ml is equal to 1 cubic centimeter. I'm asking you to remember that. It's just easy. And of course the next conversion, that 1 grain is equal to 65 milligrams, those you don't have to memorize that. You get it from the tables. And I have converted that into grams. So 1 grain is equal to 0.065 grams because our density here is grams per ml. Basically here I have 0.065 grams per grain, correct? So I just took this unit here. Also, 1 fluidance is equal to 29.57 ml. Again, you don't have to memorize. This information is on the tables. You can get it easily, but you have to convert it also into a conversion constant. So that would be 29.57 ml per fluidance. So now we're ready to proceed to carry out the conversion. So the density is 1 gram per ml. Here we are. I divide it by 0.065 grams per grain, and the denominator I divided by 29.57 ml per fluidance, as you can see here. Carry out the algebra and you see that the density of the water is 1 grams per ml, and that's equivalent to 455 grains per fluidance. If you're asked to provide the specific gravity of the water, that's not going to be 455. Specific gravity of the water is 1, because it's always expressed in gravimetric units. Okay, and this example 3.3 is dealing with the third objective, which is basically learn how to calculate the specific gravity of a liquid pharmaceutical formulation or dosage form. So here we have our formulation of drug X olive oil, talc, and purified water add up to 15 ml. We know how much olive oil we have in the formulation, that's 10 grams. We know how much talc we have, that's 4 grams. Purified water QS at 15 ml, but it says here that you are adding exactly 5.4 ml of water, and since the density is 1, that's equivalent to 5.4 grams of water. So I also know how much water I added. I don't know how much drug I added. I just know the concentration of the drug in the lotion. It's asking you to calculate the specific gravity of lotion, and we know that the specific gravity of lotion is equal to the mass of lotion over the volume of lotion. Now the mass of lotion is not known. We don't know it yet because I know the quantities of 3 ingredients, but I know the quantity of drug X. But I know the volume of the lotion, that it's 15 ml. So this I know. So the question is, how do we deal with this now? Okay, you are given the concentration of the drug for a reason. So think about it. First of all, we should explain what it is. So this 25% weight per weight, I understand that the explanation of units of concentration comes in the next chapter. So that would be the exact definition is 25 grams per 100 grams of lotion, of mixture. So that's 25 grams of drug over 100 grams of lotion, drug included. Okay, so this is the definition. And this is actually your basis for solution. So what I'm asking is, like, this is given for a reason. Make an equation out of it. Have a restless mind. Make it fun for you so you can get a satisfaction out of it. Now, also one may wonder, I mean, would a physician write a prescription like this? Of course not. Their emphasis is different, right? They are mostly involved in treating the patient, diagnosing the patient. But as a formulator, quite often I would say actually that you have in mind the concentration of the drug in the final formulation first, and then you work your way down the numbers to determine how much quantity you need to add. For example, in order to prepare a syrup of 67%, for example, right? So this is not uncommon for a formulator, for a pharmaceutical scientist. It's quite common. Okay, and this is not only here. If you are in pharmacokinetics, for example, you see that how do you calculate the dose for a patient? So there you will also realize that as a pharmacokineticist or a pharmaceutical scientist, you think in reverse. You first decide of the dosage interval, and then you work out your way to determine the dose. So let's get back to our problem though here. Based on this definition here, on this definition for the 25% weight per weight, this is the drug concentration in the final dosage form. So I have 25 grams of drug. I'm just going to write drug here, over 100 grams of lotion. And it will help me figure out the grams of drug X in the lotion. So how many grams? I'm just going to create another column next to that here, and I'm going to write the quantities of each ingredient. So definitely for olive oil I have 10 grams. For talc I have 4 grams. For water I have 5.4 grams. And for drug X, I don't know how much I have, so I'm just going to write X. And then I'm going to add all of them, and that would be 19.4 grams plus X. So I'm going to write X plus that. Okay, so my denominator, which is the mixture in lotion, that would be x plus 19.4, and my numerator, which is just the drug, is x. So now cross multiply to determine the drug, determine x. So I have 100x is equal to 25x plus I have 25 times 19.4. That would be 25 times 20, which is 500, minus 25 times 0.4, which is 15. So that would be 485. So 75x, I'm going to write it here conveniently, is equal to 485. And therefore x is equal to 485 over 75. I have to use my calculator now. So that would be 6.467 grams. I'm just going to add to that the 19.4 grams, right? Now that I have the drug, so plus 19.4 grams. So that would give me 25.867 grams, and divide by the whole volume of the lotion. And I need to use my calculator again. Oh, sensitive screen. That would be 1.725 grams per ml, and that's your grams per ml here. Okay, so that's your specific gravity or density of the lotion. You can see how a complicated problem became very easy by realizing that the concentration of the drug there, this statement here, this parameter, is actually your basis for solution. You construct an equation out of it, and then you solved it for x, calculate the drug, added the remaining ingredients, the other ingredients to that, divided by the whole volume, and calculated the specific gravity of the lotion. Nice. Here I've included the solution for you to read it at your own time. No rush, right? And I have also included 2 practice exercises as a homework. So question 3.7 is asking you to calculate the volume difference in milliliters of 2 ounces. So that's a unit for solids. So that would be 2 times 28.35 grams. Again, you don't have to memorize this. I just look it up from tables. So the volume difference between water and ethanol. So you need to convert first the solid, the mass, into volume, and then take the difference from the volume of ethanol. And of course 3.9 is identical, similar to the example that we've just solved. At this point, I would like to thank you for your attention. Until next time.